Hi, this is David Nguyen, co-founder and CEO of Brain Technology and inventor of the LCPC transform. In this presentation, we're going to talk about measuring shapes of droplets without using contact angles and how the LCPC transform provides so much more depth of information than contact angles. So contact angles are typically measured at the interface of the liquid droplet and the physical surface. And it is this angle right here, one on each side of the droplet. In this presentation, we'll talk about applying the LCPC transform to 4 cases of drop shape analysis: sessile drop analysis, tilted drop shape analysis, ricochet drop shape, as exhibited in this image of here of the liquid bouncing off the surface. And lastly, I'll talk about pendant drop shape analysis. First, how does the LCPC work? Well, you have to outline the outer edge of your shape, in this case, this droplet, and we define an origin for our radial grid. And the origin, in this case, defined as the midpoint between the line that connects the base. And in step 2, we define that origin as the origin of the radial grid from which radial lines extend 180 degrees spaced every 5 degrees. We then calculate the intersection, or every single intersection's distance to the origin, right, as can be seen in step 3. In step 4, which is optional, you can linearize it into 2 dimensions. And we did this simply for illustrative purposes, but you can go directly to step 5 without doing step 4. So in step 5, you just do fast Fourier transform on the data from step 3 or 4 to get a frequency plot, which is a multi-dimensional representation of the shape that you started with. And if you want to derive one scalar value representing the shape, you can sum all bins, or all the bars are in each of these bins together to get one value. And that one value represents the shape that you began with. To start, we analyze sessile drop shapes. And here I created a 2 series of phantom shapes. For shapes 1 and 2, they have the same height, but they're just stretched wider. Right? Shape 2 is stretched wider, and this can represent 2 different volumes of the same liquid. For the bottom images, shapes 3, 4, and 5, they represent droplets that are stretched out and flattened at the same time, right? So decreasing height and increasing width. So when we applied the radial grid system to these shapes and we summed all the bins, we see that in the first 2 bins, shape 1 and 2, you see an increase in the sum of all the bins, right? Which makes sense in that here you have this shape that is the same height in shape 2, but just stretched out more wide. And if you look at shapes 3, 4, and 5, you see an increase in the sum of all the bins, right? And so, which is also interesting, or very interesting, because in this case here, the shape as it widens and flattens, right, you also get an increase in the magnitude of all the sum of the bins, right? And so you see that this method just shows something, a form of information about shape that contact angles just cannot do. So if you take a bird's eye view of all these FFT plots, plotted to their relevant scales, what you see is that as the object deviates from the perfect semicircle here in shape 1, as it deviates either it's just in 1 dimension in width, or it deviates in 2 dimensions, height and width, you see that that deviation activates the bars in the bins other than bin 1, right? As you can see here, right, bins 2 and on begin to be activated here. All right, it's hard to see when the graphs are scaled to this degree. So let's zoom in, and when you zoom in by truncating the y-axis, you see even more insight up here. As you see that in these shapes here, 3, 4, and 5, as the droplet flattens and widens, what you see is that the last 3 to 4 bins shows an increasing exponential pattern. Right, and that exponential pattern captures the fact that the shape is widening and flattening at the same time, and is this pattern that can that allows the investigator to create an index. For example, you could sum all these bars, or you could fit an exponential curve to say the last 5 bins, and you can compare the coefficient of the exponent as an index, comparing these 3 shapes, right? That is if you wanted to derive a scalar value, right? That's another way of doing it, fitting an exponential curve. And so this again goes to show the depth of information that the LCPC transform extracts from seemingly basic shapes. Moving on to tilted drop shape analysis. So in a tilted drop shape, the drop will lean due to gravity, and there is a advancing angle right here, and then there is a rescending angle right here. So in this case, we again applied the radial grid, and we defined the origin of the radial grid as the midpoint of the line that connects the base of the droplet. And we applied that to these 6 phantom shapes. So I created these 6 phantom shapes to show the concept of a droplet leaning to the right. So in each subsequent shape, the droplet leans more and more to the right. The droplet in shape 2 leans slightly to the right, which may or may not be visible to the naked eye, but there is a lean. And this actually will reveal something quite interesting in the coming slides. So applying this radial grid system to these phantom shapes, right? First, we look at the bins 2 and 3, because bins 2 and 3 happen to be bins that capture these changes in shapes very well. So you see here that there is an exponential increase, right, in the magnitude of bin 2 and bin 3 as the shape goes from perfect semicircle, right, to a droplet that leans to the right. Right? In other words, a droplet that's skewed to the left, right, in terms of where the tail is pointing. But something is very interesting is that here's a very counterintuitive piece of data right here, because as you go from shape 1, which is a perfect semicircle, right, as it begins to tilt, you would expect an increase, a smooth exponential increase, but yet there's a dip in shape 2. In shape 2, there's a slight lean to the right. Right, and this slight lean actually causes a dip in the value of bin 2, right? And you see that also in bin 3. There's a dip, right, and then the exponential increase. And this dip, right, it may be an artifact to this artificial phantom system, right? Or if we see this dip repeat if we actually create or measure precise shape changes, right, in the initial shift after equilibrium is broken, right, this little dip right here might reveal something insightful about the physical properties of that liquid. That is, there might be something special about the initial phase of breaking equilibrium when a droplet, encounters a vibration or a tilt. Whatever the case, this slide goes to show that the LCPC transform can detect very subtle, changes in shape information in ways that are just beyond contact angles. If we take if we zoom in a bit by truncating the graphs, we see that as the shape tilts more and more to the right, you see an increasing activation of these bins from 2 all the way to 35. The more it leans, right, the higher these bins are. And all of these recurring shapes, if we were to have shapes representing every continuum, right, from shape 1 to 6, we could actually measure quantitatively, create an index that measures the threshold of transitions between shapes, and we might actually even find certain threshold cutoffs. Zooming in even further, we see that there are distinct. We see further the distinct shape of the bins, representing the leaning of the droplet towards the right. Alternatively, I want to point out that the LCPC transform does not require that you measure the full shape. In fact, we could measure just the front end, that is the leading edge. Here, I just define the apex of the droplet, right, as a dividing line, which would allow us to then objectively define the front edge in every droplet. And in this case, we can apply the parallel grid system to measure the shape of just the front end. and then just measure, apply LCPC just to this part, this compartment of the drop. You could do the same for the tail if you want to study the skew. Now for drop shape analysis of liquids that are not homogeneous, that is, you have particles inside, or you have nanobots that can be programmed to swim towards one end, right? You can then measure just particular compartments of the drop shape to test the property of that liquid in homogeneous, non-homogeneous circumstances. Moving on to ricochet drop shape analysis. In this study by Howe et al., they measured the shape of this liquid as it contacted the surface and then deformed and then rebounded off of the surface. And we thought that this was a good study to analyze because clearly these transition shapes have information that contact angles simply cannot see. Right. In each of the cases where these droplets contact the surface, you can measure Young's angle, the contact angle. But clearly, there's a lot more information in the shape that Young's angle cannot assess. So, for these shapes, we define the origin as the centroid of the shape, and we use a 360 radial degree radial grid instead of a 180. And here, if you sum all the bins, right, you compare the sum of all bins for each shape, you see an increasing value, okay, magnitude for each of these shapes as they deviate further and further from the original droplet, which is a somewhat near perfect sphere. What's interesting, and it also makes sense, is that this bar, as it increases, it drops, right? It drops as the shape begins to return to a spherical form. I guess we would hypothesize that this bar will continue to drop if we were to measure this shape, right, over time further. That as this shape returns to a sphere, you will see that this bar would drop further and further back down to where it started. Right. Again, this goes to show the depth of information that the LCPC transform can measure, right, beyond that of contact angles. If you zoom in, right, you see that this is actually a bird's eye view because we did not scale the graphs to see the smaller bins. But you already here you can see that for elongated shapes, whether horizontally elongated or vertically elongated, the last few bins, right, exhibit, okay, that characteristic. Zooming in, by truncating the y-axis, we see again that theme, right, more vividly. That is for shapes that are vertically stretched, as in these two, you see this exponential increase in the last few bins, right? And while for shapes that are horizontally stretched, the pattern is actually a cliff, right? You peak and cliff, as described up here in this graph. You see that peak and the cliff. So there are patterns that if you were to measure the continuum of shapes between each of these, I guess, milestone shapes, you'd be able to quantify these patterns in the form of indices that show clear thresholds that define shape categories. Lastly, let's talk about pendant drop analysis. So in this study, the authors attached two liquids to each other and then measured the angle between the surface of these two liquids. And they did that by fitting the Young-Laplace equation, which allowed them to calculate this angle, right, at the interface of these two liquids. The study went on to test two different systems of liquids, whether in air or in a further liquid, showing that as you extrude and retract the top liquid, right, its shape changes as it is pulled on by the bottom liquid. So here I just want to point out that for pendant drop shape analysis, right, I think a good grid system would be the parallel grid system, right, measuring just one side. We're assuming that both sides are symmetric. And this allows you to compare both liquids, okay, to each other, or just the first liquid to each other, or just the bottom liquid to each other. In any case, the LCPC transform will reveal deeper insights into pendant shapes than will contact angles. So in summary, here are 7 generic ways through which people analyze drop shape. And in each of these cases, the LCPC transform can measure surfaces with much deeper information, or much more deeply than simply using contact angles. There are many use cases of drop shape analysis, and in each of these use cases, the LCPC transform is poised to revolutionize how much information can be extracted. And in my opinion, in the coming 5 to 10 years, the LCPC transform will replace contact angles, or at least make contact angles seem very archaic. And as an aside, other applications that are not directly related to drop shapes, but still include liquid shapes or air shapes, bubble shapes, that can benefit from the LCPC is film boiling, right? The study of how liquids boil. But liquids boil start with nucleate boiling, and eventually, as temperature increases, these bubbles fuse to form plumes, and eventually, once it reaches critical temperature, it develops into what's called film boiling. And a lot of cooling systems, whether for nuclear reactors or for massive computer towers, right, need to track AI to track the shape of bubbles so that it can give a critical warning as to when film boiling is about to happen. And this is an application that the LCPC transform can really make a big difference for. Another application is a recent study in which Google and researchers modeled the fusion reaction. And here they created simulations of plasma and how the plasma can be induced to change shape, right, and to change locations within this chamber. And the LCPC transform can measure every single blob shape with precision, and can allow the investigators to make even more refined predictions about how perturbations will affect the behavior of plasma. So in conclusion, I hope to have convinced you that the LCPC transform is poised to revolutionize how we measure drop shapes and all the applications that rely on drop shape analysis, such as waterproofing, coatings, pharmaceutical coatings, liquid-liquid interactions, liquid powder interactions, and we're real excited about all the potential applications. So if you have any questions about consulting or software licensing, please feel free to visit our website and reach out to us.